Hello everyone. So today I'm going to show you how to calculate gas laws, which is talked about in Unit 7. It's the last part of Unit 7. And it can be confusing and a little bit difficult. So let me go through some calculations with you to show you how to do those. And let's talk about some ideas with kinetic theory, which kind of lead into that, specifically more about temperature and what is Kelvin, how you convert Celsius into Kelvin. So let's go ahead and get started. So as far as gas laws are concerned, there's two different ways that you can measure temperature for gas laws. One of them is you can measure in degrees Celsius. Another one is you can measure in Kelvin. Kelvin came a little bit later after degrees Celsius because there was a scientist by the name of Lord Kelvin from the United Kingdom that said that the lowest temperature that you can actually get is what we call absolute zero. And absolute zero has been theoretically calculated to be negative 273.15 Kelvin. Now, how did they actually do that? Well, what they did is they took the idea that, okay, temperature is a measurement of how fast particles move, and that means that if they have no kinetic energy, that must be 0 Kelvin. So how do you do that? Well, what they did is they took a metal sphere, filled it with a gas, put a pressure gauge on it, and they kept dropping the temperature of it and graphing that data. They kept graphing basically the pressure versus the temperature. And what they found is that as the pressure was high, you might have a data point here, and as you keep dropping the temperature on it, the pressure would continue to drop itself. And it was a straight line function like this. And so what they did is they basically extrapolated all the way down here to when you get to 0 pressure. And when you get to 0 pressure here, that is negative 273.15 Kelvin. So that's how he figured it out, all right? Pretty ingenious way of doing it using some low-tech tools that were in existence at the time. So how do you actually do the conversion? Well, that number is important because let's say that you had something that's 80 degrees Celsius and you want to convert it into Kelvin. That means that you have to add 273.15 to that number to convert it into Kelvin, which would be 353.15 Kelvin. All right, so that's how you would convert it into Kelvin. Just add 273.15. If you want to go the other way and you want to convert something from Kelvin, so let's say it's that number, 353.15 Kelvin, and you want to convert it back into degrees Celsius, what would you have to do? You would subtract the 273.15 out. And that would give you your 80 degrees Celsius again that you started with, all right? So this is the important thing that we're going to have to be able to do because the formulas for gas law only work with positive values. So you have to convert everything into Kelvin whenever you do a calculation with it. So that's extremely important and that's key. Another concept that is talked about in kinetic theory is a concept of what's called STP and what that stands for. That stands for standard, temperature, and pressure. And they're set values. So any problem that they give you that says that the gas is at STP, what they're telling you is 0 degrees Celsius, and they're telling you the pressure is 1 atm, right? So pressure can be measured in a whole bunch of things, and so that's the next thing we talked about. We talked about temperature can be Celsius and Kelvin. Well, what about pressure? Well, pressure can be measured in atmospheres, say 1 atm, which is standard pressure. That would equal another measurement called torr, 760 torr, which is another measurement for pressure. Sometimes they don't use the word torr. Sometimes they use the word or the abbreviation millimeters of mercury, all right? So either one. Another one would be kilopascals. That's equal to 101.3 kilopascals. And then there's pounds per square inch, or which is PSI, which is what you have for the air that's in your car tires. There's a lot of different measurements, but that one's not metric, so we're not going to talk about those. These are the 3 metric ones that are typically used. And the one that's used the most is the ATM. All right. So let's go ahead and start talking about some of these gas laws. So the first one I want to talk about is what's called Dalton's gas law. And Dalton's gas law has to deal with something called partial pressures. Basically, the partial pressures add to a total pressure. That makes sense, right? So let's talk about an example of that, all right? Let's say that you have a scuba tank and you need to have it refilled. And so you take it and then they charge it for you. They put the appropriate gases that are needed within it. And let's say that the pressure gauge on the tank now says that it's 100 ATMs of all the gases that are in there. Now, what do they put in that tank? Well, they put a couple things. Of course, they put oxygen in there because that's what we breathe. So let's say if they put 40 atmospheres of oxygen in there. Another one that they put in there is nitrogen because most of the atmosphere is made out of nitrogen. And that's usually a larger quantity. Well, that's always a larger quantity. Let's say that it's 50 ATMs. And then there's another gas that they put in there to help decrease the probability of your body getting something called bends, which is a really dangerous situation to be in if you start to rise to the surface after you've been underwater for a long period of time. The gases that are in your bloodstream can actually boil and create air pockets, and then when that hits your heart, you can have a heart attack and die. Usually, you have some symptoms of it. You start to get some joint pain, stiffness in the joint, and then so divers typically will use a watch that gives them a warning if the pressure is changing too quickly as they're surfacing to the surface. So there's things that help prevent that. But in addition to that, they use helium. We found that helium helps to decrease the probability of getting the bends in a tank. Okay, so what formula do you use? Well, the total pressure, or PT, is equal to the sum of all the gases that would be in that tank. So let's say there's only two gases, then it would be pressure 1 plus pressure 2. Let's say there's 3 in there, like what we have right now. Well, then it would be P3. Maybe there's 4 gases, so plus P4. So this equation can continue to grow. So I'll put some dots after it, meaning that it could repeat depending on how big it is. So let's fill it in. The total pressure is 100 ATMs. The pressure of one of the gases is 40 ATMs. We'll say that's our first gas. Let's say our second gas is the nitrogen at 50 ATM. And then the third gas we don't know, that's the helium. So let's, instead of maybe using a P3, let's use HE. So what would you have to do? It's very simple, arithmetic. So 40 and 50 give you 90 ATMs plus the PHE, and then the 100 ATM. And so to solve for PHE, what would you have to do? You just take 100 and you subtract the 90 ATM, and you get 10 ATM, right? So that's how you use Dalton's law of partial pressures, okay? All right, so that's one of the gas laws that they talk about. Another one that they talk about is Boyles and Charles, and they talk about how that's derived from an equation called the combined gas law. So let's do that one. Combined gas law. Now the combined gas law is P1 V1 over T1 equals P2 V2 over T2. And you might be like, well, okay, I think I know what all those mean. P is pressure, V is volume, and T is temperature. Now, what do the 1s and the 2s mean? Well, the 2s basically mean in the future what it will be, okay? What the final volume or pressure or temperature will be. If it's a 1, they're referring to the starting, or usually when you read a problem, it'll be in past tense or it'll be in present tense. So starting and ending, or past and present tense and future tense. So that's what you want to look for. Okay, so what's interesting about this formula is that if you keep one of these things constant in here, like let's say, for example, the temperature remains the same, but you just change the pressure and the volume. So what does that mean? Well, because the equations are, the sides look equal to each other, they'll divide out of the expression. So if both these numbers are 4, then the temperatures drop out. So let's say that happens. Let's say that you have a situation where the temperature is constant. We call that Boyle's Law. Boyle's Law is where the pressure and the volume are the only things that change. And the temperature remains a constant. So T equals constant. So if T is constant, that doesn't even look like constant. Let's fix that. All right. So if T is constant, then it drops out of the expression. You have P1 V1 equals P2 V2. Another one that you could have would be like Charles's law. And in Charles's law, Charles did some experiments where he kept the pressure constant. And if you keep the pressure constant, then the P's will drop out of the expression. So you'll have V1 over T1 equals V2 over T2. All right, so let's go ahead and just kind of go through some problems using either one of those. So let's say for Boyle's law, let's say that you have like a balloon. And in that balloon, you basically have it filled with just regular air in that balloon. And let's say that the starting pressure, let's say that it's STP, it's under conditions of STP. Remember what that means? It would be 1 atm. Temperature would be 0 degrees Celsius. And then the volume would end up being 100 milliliters. And then they tell you that the pressure changes. Let's say it goes up to 2 atm, but the temperature stays the same. If it's 0 degrees Celsius, we don't need that information in the formula. And then the last piece of the puzzle is what happens to the volume. So let's go ahead and plug all our numbers in here. So we have 1 atm goes in for the present tense, what it is right now, and the initial volume is 100 milliliters. And then the pressure changes to 2 atms, and we want to see what happens to the volume. So this is just basically algebra. This is like having a problem where you have 4 times 2 equals 2x. And how would you solve that? Well, you would just say 4 times 2 is 8. And to get x, you would just take 8 and divide it by 2, and that would give you your 4. So we're going to do the same thing. 1 times 100 is 100. Now look what happens to the units, though. It's atm times ml. And then over here you have 2 atm and V2. And if we take this and we divide it by the 2 atm, what happens? The atm will now be underneath here, and they'll cancel. The atms will cancel, and you'll be left with a unit measurement of milliliters. And 100 divided by 2 is going to give you 50 milliliters. So basically, what does this tell you? It tells you that if you have a pressure increase, then the volume is going to actually drop on you. So it's an inverse relationship. Pressure goes up. What happens to the volume? It drops, okay, which is basically what Boyle's law says. Now let's go ahead and take a look at Charles's law. So let's say that we have another situation with a balloon. And let's say that on that balloon, let's say that the volume that you start with is also 100 milliliters. And let's say that the temperature is 20 degrees Celsius. And the pressure is going to be is a constant. Let's say it's 1 atm again, or let's change it. Maybe we'll make it 4 atm. And then as far as the final volume is concerned, let's say we don't know what that is. We're trying to figure out what that is. And let's say that the final temperature increases to 40 degrees Celsius, and then the pressure ends up remaining consistent at 4 atm. So if that happens, you know that you're not going to go ahead and use that in the expression. You can go ahead and plug all your numbers in here. So you have 100 milliliters as your starting volume, and then your starting temperature is 20 degrees Celsius. Don't forget, you have to add 273.15 degrees Celsius to that number before you can go ahead and you can stick that into the expression. So that would end up being 293.15 Kelvin. And then on the other side, we don't know what that new volume is going to be. But let's say that the temperature then goes up to 40 degrees Celsius. So again, you have to make sure you add that 273.15 onto that number before you go ahead and you stick that into that expression. So that means that the temperature is now going to be 318.15 Kelvin. So let's go ahead and do our math there. So how do you do this? When it's set up like a proportion, you do what's called cross multiply. You cross multiply the numbers that are diagonal from each other, so the 100 times the 318.15, and then divide, and you divide by the other, which would be the 293.15. When you cross multiply those two and you divide by the 293.15, the K's will end up canceling out, and you'll be left with milliliters as your volume. And so your final volume will be 106.7 milliliters. So let's see what the trend is there, all right? If your temperature goes up, what happened to the volume? The volume went from 100 milliliters to 106.7. So it's a direct relationship. It also went up, okay? So Charles, if the temperature goes up, the volume is going to go up as well. All right. So now let's move on to the last piece that they talk about. And that last piece that they talk about has to deal with something called the combined gas, or not the combined gas law, but the ideal gas law. All right, so when you're talking about the ideal gas law, it has a pretty funky equation. It's PV equals nRT. Now, what do those components all mean? Well, T is temperature, V is volume, P is pressure, you know that. R is a constant, and N stands for the amount of moles. So you knew that was going to come back to haunt you, right? Okay, the moles. So whenever you go to use combined gas law, you want to make sure that you know what the value is for R. Now, the R value is a constant number. It will never change. It's always going to be 0.0821 liters times atmospheres divided by Kelvin times mole. I like to use the analogy. It's kind of like the acceleration due to gravity. You guys all learned whenever you took your physical science, your integrated science, that's 9.8 meters per second squared. It's always that. It's the same thing for R. It's always going to be this value if you're talking about liters, atmospheres, Kelvin, and moles. It's always going to be that value that you stick in there. So let's say that maybe you have a problem that you start with this. And the other information that they give you, well, let's say they want you to find volume again. All right. And let's say the other information they give you is they give you the pressure. They say it's at standard pressure, which would be 1 atm. They say it's at standard temperature, again, STP. That would be 0 degrees Celsius. Don't forget, you want to add 273.15 to that number and convert that number into Kelvin. Well, there you go. That's easy, 273.15 Kelvin. And let's say that they give you 100 grams of water vapor. Because keep in mind, we're talking about gases. So this gas is heated. Water is normally in the liquid state, but when it's heated, okay, it's in the gas state. Well, let's say you have 100 grams of that. Well, the first thing you're going to have to do is you can't use grams in here for moles. So what do you have to do? You got it. You have to do a one-step mole problem. Start with 100 grams of water. If you need your mole mat, you can grab it, or just know that grams of water is going to go down here. And then what would be up top would be 1 mole of water. So you need the atomic mass for water. That's 18.015 grams. And that will convert it into moles for you. If you do that math, you're going to end up with a number of 5.55 moles of water vapor. So we're going to use that in our equation. So 5.55 moles, and then the R value is 0.0821 liters times ATM divided by K times mole. And then the temperature is going to end up being 273.15 Kelvin. And then over here, the pressure is 1 atm. And then we're looking for the V. So let's simplify this expression. We're going to take 5.55 times 0.0821 times 273.15. And all of that together is going to give you a number of 124.46. Now look what happens. You get some canceling going on here. The kelvins are gone. The moles are going to be gone. And you're left with liter times ATM. All right, so that's one side. On the other side, you have 1 ATM still, and you have your V. So what would you do? This is like solving a problem where you have 2x equals 4. How do you solve for x? Take 4 and divide it by the 2, and you get 2. So do the same thing. Here's your number. Here's your number. You're going to divide it by the 1. In this case, we divided it by the 2. So 124.46 divided by 1 is the same number, 124.46. Now look what happens. The ATMs will end up canceling out because this ATM's now over here in the denominator when you divide the 2, and you're left with just liters. So that is your answer. Right. So hopefully that helped you out. Those are all the different types of gas laws that the apex, the last part of Unit 7 talks about. And so now you got some examples to go by. Hopefully you have a little better understanding about Celsius and Kelvin and what those gas laws are to help you through the rest of those problems. All right, have a good evening, everybody. Take care. Bye.